So, dear colleagues, I greet all of you from Kiev, Ukraine, and I thank these organizers for the invitation and the possibility to give a talk remotely. Today, I'm happy to present a talk about geometry-governed effects in curvilinear magnetism. There is a connection with a very exciting previous tutorials and talks, which we already heard today. My talk is mostly related to the tutorial by Denis, who presented a very nice overview of curvilinear magnetism and demonstrated its numerous applications. And during my talk, I will try to provide the recent progress, challenges, and prospects of curvilinear magnetism, with a special focus on novel physical effects caused by favoring geometry of conventional magnetic materials. So, curvilinear magnetism is a very young and modern direction in magnetism. The first review of curvature effects in magnetism appeared 8 years ago only. And during these 8 years, curvilinear magnetism made an impressive progress, which indicated in these review articles we were already mentioned today. And there are many examples of curved magnetic systems with numerous novel effects caused by curved geometry and non-trivial topology. And most of the results dated by 2022 are available in this book. Let me first briefly discuss the source of imagined physics of curved magnets. Typically, flat magnets possess special inversion symmetry. For example, top and bottom surfaces of a flat film are identical. The inversion symmetry becomes broken if we bend the film. And namely, this broken symmetry is a source of imagined interactions, geometry-governed anisotropy and chiral interaction. And these interactions result in new geometrically magnetochiral effects, which we will discuss today. The picture becomes more intriguing if we modify a global geometrical process, namely the topology. For a non-trivial topology of the surface, there appear topological effects, in particular new magnetic textures. As a consequence, we get an effect of topological patterning. Let me start from the typical model of a classical ferromagnet, which includes exchange, anisotropy, Dzierzhinsky-Mourier interaction, and magnetostatics. How does the curvature get into the game? First, we simplify the model by considering exchange and anisotropy only. This local model cannot describe all the curvature effects, but we can follow basic ideas. And besides, this model is quite general, being Ginzburg-Landau model for the vector order parameters. And commenting the question by Amalio, I would like to say that these ideas which we consider, they can be applied to a variety of condensed matter systems, including not only magnet, but liquid crystals and superconductors, as was mentioned by Stuart and Denis. In this model, the influence of curvature appears through the special dependent anisotropy, and the direction of anisotropy axis fills the curvilinear geometry. For example, typically the anisotropy axis for the thin wire follows its shape. And in case of curved film or shell, the anisotropy is typically determined by the normal direction, which becomes coordinate dependent for the curved film. And namely, the geometry-dependent anisotropy becomes a source of new effects. And one more consequence, if the anisotropy is strong enough, it dictates the assumable magnetization distribution. And thus, the geometry indicates that the behavior of the magnetization structure should be considered in the curvilinear reference of frame, which is adopted to the geometry. And the geometry broken symmetry leads to a restructuring of magnetic energy terms containing special derivatives, as was already mentioned by Denis. An exchange interaction which is isotropical is a Cartesian reference frame, transforms now into three components in curvilinear coordinates adopted to the geometry. In addition to the common part, there appear geometry-governed anisotropy interaction, and the coefficient of the effective anisotropy are determined by the principal curvatures. And the most interesting and intriguing additional interaction is the geometry-governed Zeroshinsky-Morier interaction, which is responsible for the symmetry break. And it has a form similar to the well-known Zeroshinsky-Morier interaction with consequences such as helical structures and skyrmion crystals. An important message is that there exists one more mechanism, the geometrical one, for the Zeroshinsky-Morier interaction. I am not able to refrain from the mentioning an attractive analogy with the classical mechanics. The motion of a massive particle in a non-inertial reference frame is always accompanied by additional energy contributions and corresponding forces, centrifugal force and the Coriolis force. In classical mechanics, these two imagined interactions result in numerous physical effects. That is why it is interesting to look for the physical consequences of these two imagined magnetic interactions. We already mentioned two emergent interactions, Zeroshinsky geometry-governed anisotropy and geometry-governed Zeroshinsky-Morier interactions. And now we discuss the effects related to these interactions. And the first class of effects is called a topological pattern. This means the formation of topologically protected magnetization textures in topologically non-trivial curved geometry. It appears when the emergent interaction does not break the spatial symmetry. For example, it can be caused by emergent anisotropy, but not necessarily. Let us start from a flat magnet, where the magnetization state can be uniform or quasi-uniform if the object is small enough. Instead, that tangential magnetization distribution in a spherical shell can never be homogeneous. Two vortices are formed on a sphere. The reason is both curvature and topology, namely the Hairy-Ball theorem. In the case of thin spherical shell, the anion state is mainly caused by exchange interaction, while the Volygic state for the thicker shell appears due to the magnetostatics. A tubular geometry supports vortex and transversal domain walls. The symmetry of toroidal shells support toroidal and poloidal vortices. Hyperboloid shell favors vortex and skyrmion textures. A topology of non-orientable Möbius ring plus different topologically protected domain walls. The next group of effects is a geometric magnetic-chiral effects. One can distinguish two typical situations when magnetic-chiral symmetry breaking occurs: pattern-induced chirality breaking and geometry-induced chirality breaking. On this slide, you see the pattern-induced chirality breaking. It takes place when the symmetry of the system is so high that magnetic states with opposite chiralities are degenerated. For example, straight cylindrical nanotubes support two energetically equivalent vortex domain walls with different chiralities. And the break of magnetic chirality occurs dynamically, and it is driven by magnetostatics. For example, vortex domain walls are sensitive to the direction of the external magnetic field with respect to its chirality. One wall moves faster than another one, which results in the chiral breakdown. And the chiral symmetry break is connected to another interesting effect: suppression of the worker breakdown. leading to Cherenkov radiation of magnets for the fast domain walls. One more consequence of the pattern-induced chirality breaker in the non-reciprocal spin wave dynamics. There appear an asymmetry in the dispersion law. Now the geometrically induced chirality breaker. It is a consequence of an interplay between geometrical chirality of the object and magnetic chirality of the texture. Chiral interactions can select handedness even for a non-chiral texture. That is why the curvature-induced Delshinsky-Marie interactions shows itself in the curved flat magnetic system, provided this phase-selected pinning of the domain walls in a flat parabolic stripes, outward for head-to-head domain walls and inward to tail-to-tail ones. And the strengths of emergent Delshinsky-Marie interactions was quantified experimentally by measuring the dependent field. The emergent Delshinsky-Marie interaction in helix wires supports a coupling between the geometrical helix chirality and the magneto-chirality, providing the preferable handedness of the domain wall. In a helicoid ribbon, an imagined Delshinsky-Marie interaction selects the preferable magnetization handedness of the ground state. Besides, the imagined Delshinsky-Marie interaction is responsible for a specific remanent vortex-anti-vortex states in a hollow toroidal nanomagnets. For a curvature-induced selection of the winding number of a meron in different nanoshells, while the vortex state is supported by the parabolic geometry, the anti-vortex is favorable for the hyperboloid shells. The spherical shell can support a skyrmion stabilized by Delshinsky-Marie interaction governed by geometry. One more example of the interplay between curvature, magnetic order, and additionally non-trivial topology occurs in magnetic Möbius rings. Geometrically, there exist two types of Möbius rings, right and left, which can be characterized by the geometrical chirality. Different magnetic configurations in the Möbius ring can be realized depending on the geometrical and material parameters. One of the topologically non-trivial state appears if we magnetize the Möbius ring perpendicularly. Then, due to the topology, we have a discontinuity in the magnetization distribution. And finally, we get the so-called topologically protected domain wall. And this wall is characterized by its magnetic chirality, which is direction of the wall, inward, like in this picture, or outward. And the emergent Delshinsky-Marie interactions break this chiral symmetry, and magnetic chirality becomes coupled with the geometrical chirality. And recently, magnetic Möbius rings were fabricated using Fabit technique, as was described by Amalia. An intriguing geometrical magneto-chiral effect is caused by exchange-driven Delshinsky-Marie interaction. It can be applied for such topological magnetic textures as a skyrmion. There are two different mechanisms of the geometrical stabilization of the skyrmion. Small radius nail skyrmions can be stabilized by a mean curvature of the curved shell without intrinsic chiral interactions. At the same time, tunable radius skyrmion, in particular large radius skyrmion, can be stabilized by the gradient of the curvature. And these theoretical predictions correspond to experimental studies. In particular, self-organized patterns of nanocones and spherical indentations were used as templates for deposition of magnetic films with out-of-plane anisotropy, and magnetic states in such systems reveal a strong correlation between the magnetic texture and the geometry of the substrate. The next consequence of the magneto-chiral effects is the so-called mesoscale Dzerzhinsky-Murray interaction. The idea is the following. Two types of Dzerzhinsky-Murray interaction, intrinsic one, caused by magnetic parameters, and extrinsic one, caused by the geometry, curvilinear geometry. They influence magnetic texture acting at different length scales. And it is important that the symmetry and the amplitude of the resulting Dzerzhinsky-Murray interactions are determined by both material and geometrical parameters. And this offers possibilities to tune both magnitude and direction of the mesoscale Dzerzhinsky-Murray interaction by pure geometrical manipulations. One of such possibilities is a concept of artificial magnetoelectric materials, where the magnetic state is efficiently modified due to the change of geometrical parameters of the curved nanomagnets. Localized curvilinear defects can favor the multiplet of Skyrmion states, with perspective to be utilized to encode and switch a bit of information. The periodically arranged lattice of the curvilinear defects can generate a Skyrmion lattice as a ground state, when the Skyrmion radius is comparable with the size of a curvilinear defect. Most of effects which we already discussed before were limited to the local interactions, such as Heisenberg exchange, anisotropy, and Dzerzhinsky-Murray interaction. And moreover, if we speak about flat magnets, there are no chiral non-local effects at all. In order to understand the non-local physics of curved magnets, it is useful to describe the magnetostatic interactions by three fixed charges. It was already mentioned by Denis Makarov. And I would like to mention that these three charges are tangential charge, geometrical charge, and surface charge. The tangential charge is determined by the tangential magnetization components only. It coincides with the well-known volume magnetostatic charges in flat magnets. And the new guy is this geometrical charge, which is determined by the local characteristics of the curved surface, its mean curvature, and properties of magnetic texture. And it couples the magnetic subsystem, the normal components of magnetization, with the curvilinear geometry, with the mean curvature of the system. And very recently, this effect was studied both experimentally and theoretically for the vortices in asymmetric permalloy caps. The non-local chiral symmetry breaking effect in this object leads to the geometric deformation of the vertex string into the helix. The geometrical chirality of the vertex string is determined by the magnetic helicity of the vertex texture. And it's tricky that there appears a coupling of two chiral parameters with the same texture. And now I would like to mention few prospective directions. Among fundamental directions, I would like to mention a curvilinear antiferromagnetism and magnetism of materials with varying cross-section. Among numerous applications of curvilinear magnetism, I mentioned shapeable magnetoelectronics, curvilinear spintronics, curvilinear magnonics, skyrmionics, and magnetic soft robotics. Curvilinear antiferromagnetism is young enough field, so the concepts of curvilinear antiferromagnets was introduced 3 years ago for one-dimensional spin chain. As opposed to the ferromagnets, the single ion anisotropy in antiferromagnets leads to the homogeneous Dzerzhinsky-Murray interaction. And that is why the curvilinear antiferromagnets behave like weak ferromagnets. And finally, the intrinsically achiral one-dimensional curvilinear antiferromagnets behave as a chiral helimagnets with geometrically tunable Dziewoszynski-Morier interactions. And geometry-induced Dziewoszynski-Morier interactions becomes a source of spin wave mode hybridization.
Denis?
Yes.
Denis? Sorry,
Yeah.
if the screen's gone blank, if you wait 2 seconds, we're just recovering the connection.
Okay.
Sorry to interrupt. Okay, you're back. You can continue. Thank you.
Okay, perfect. Yeah, thank you. And perspectives of curvilinear antiferromagnetism are discussed in details in this recent review. And already was mentioned by Denis Makarov. I will mention here that curved antiferromagnets at the moment are treated classically without account of effects of frustration, quantum effects, and magnetoelasticity. So it will be the future of this direction. And one more very new direction in curvilinear magnetism is a control of magnetic response by tethering the cross-section. I start with the problem of geometry-induced automotion of domain walls. The first theoretical step in this direction was achieved by a concept of geometry-induced motion of earlier spiral in a nanostripe. The first experimental steps includes the domain wall automotion in Archimedeal spirals and the three-dimensional helical domain wall conduits. In experiments for 3D interconnectors, which were already mentioned by Amalio, there is a highly specially varying thickness gradient during the 3D nanopatterning using Fabit. And namely, this thickness gradients was expected to be a dominant mechanism of experimentally observed domain walls automotion in 3D interconnectors. And that is why the question of the role of varying cross-section is of special interest. Very recently, we have extended an existing theory of curvilinear magnetism for wires and stripe with varying cross-section. And the output of the theory is the following. The gradient of the cross-sections acts similar to the gradient of the curvature, causing the chiral interactions. We applied these results to predict the effect of the statics and linear dynamics of domain walls in curved stripes with varying cross-section. In particular, domain wall can be pinned by a local cross-section deformations. Here you see the parabolic stripe, whereas the maximum of the curvature, this green line, does not coincide with the maximum of the cross-section, this blue line. And finally, the domain walls is pinned somewhere in between this magenta line. And now by applying external magnetic field, works, wait a minute, okay. Now if we apply external magnetic field, we can excite the oscillations of the domain walls at this pinned potential. And the frequency of these oscillations are determined by both curvature and cross-section gradients. Another very perspective direction is the problem of the topological excitation dynamics in a curved racetrack. So it was at talk by Stuart, previous talk by Stuart. And now I would like to mention a skyrmion dynamics in a curved racetracks, the so-called curvilinear skyrmionics. It is possible to...
Denis,
yes,
Denis, sorry, you're almost out of time, so maybe 1 minute or so. Would that be okay?
Yeah, okay, so it's the last slide, yeah. So I would like to mention here that just it is possible to excite skyrmion eigen oscillations, which results in the skyrmion gyro motion with characteristics determined by the curvature on the shell. And similarly, domain wall transport to domain wall transport, one can excite the skyrmion automotion, in particular the curvature-induced drift of skyrmions under the action of curvature gradients without external stimuli. And the current-induced skyrmion dynamics becomes very sensitive to the curvature of the racetracks, and the tubular geometry provides the way to eliminate the drawbacks of the skyrmion Hall effects. And with this, I would like to finish. At the end, I just want to acknowledge several groups. First, I thank our written team, which is a joint group between the Kyiv University and the Kyiv Institute for Theoretical Physics. And I mentioned here colleagues who are originated from our group and who participate in this curvilinear activity. And also, I'd like to thank several other groups by Denis Makarov, Yaron van den Brink, Avat Saxena, Petra Landeros, and Valery Slasnik. Thank you for your attention.